May 1977. At the Dounreay nuclear facility in Scotland, a 65-metre shaft sealed by a concrete lid held 2 decades of radioactive waste. But deep below the surface, an unseen chemical reaction was turning the repository into a pressure vessel. The forensic record of this event reveals a catastrophic procedural lapse and radioactive fallout still being measured today. 1959. Caithness, Scotland. The United Kingdom Atomic Energy Authority made a decision that would define the next 70 years. A vertical shaft, 65.4 meters deep, originally excavated to construct an offshore tunnel, was repurposed. The tunnel project was abandoned, the shaft remained, and someone decided it was an acceptable repository for intermediate-level radioactive waste. This was not a temporary measure. For 18 years, workers disposed of contaminated material into that sealed underground cavity. Equipment, tools, reactor components, coolant residue, and reactive metals, sodium and potassium, stripped from decommissioned systems. The disposal method was unsophisticated, material was lowered or dropped, the shaft filled slowly, layer upon layer, in complete darkness. But here's the procedural lapse. The shaft already contained seawater, residual fluid from its original construction as a marine access tunnel. The authority knew this. The disposal continued anyway. Sodium reacts violently with water. Potassium does the same. Both metals generate hydrogen gas on contact. In open air, the gas dissipates. In a sealed 65-meter pit, it accumulates. The headspace above the waste, the narrow column of air between the surface of the material and the concrete lid, became a containment zone for an invisible, flammable atmosphere. No monitoring system tracked the gas concentration. No ventilation system existed. The lid was a static barrier, not an engineered seal. It was a simple concrete plug weighing several tons, designed to keep material in and weather out. By May 1977, hydrogen saturation in the shaft headspace had reached the flammable range. Between 4 and 75% hydrogen-to-air ratio, the mixture becomes explosive. Any ignition energy, a spark, a static discharge, a hot surface will trigger detonation. The shaft had become a vertical bomb casing, and nobody at Dounreay knew. The site operated normally. Personnel conducted routine maintenance. Waste management procedures continued at other facilities. The shaft itself was dormant, sealed, forgotten, unmonitored. Consider the scale of the oversight. Every week, site operators logged disposal events, material mass, waste classification, estimated activity levels. But nowhere in those records did anyone calculate cumulative hydrogen generation. Nowhere did anyone model gas accumulation in a sealed vertical column. The risk assessment didn't exist. This wasn't willful negligence, it was institutional blindness. The shaft was out of sight, the chemistry was out of mind, and the consequence was a pressure vessel, 18 stories deep, venting into nothing, building toward critical mass. The only question was ignition timing, until the ignition source arrived. May 10, 1977, a routine operational decision activated a water pump connected to the shaft drainage system. The pump's function was mundane: manage groundwater intrusion, prevent flooding in adjacent tunnels. Standard procedure, the kind of task logged in a maintenance report and forgotten by the end of the shift. But pumps generate heat. Electric motors produce sparks during startup, especially in older industrial equipment. The 1970 Dounreay site used systems installed decades earlier, machines designed when hydrogen accumulation in sealed waste repositories was not a recognized hazard. The forensic analysis is unambiguous. The pump activated. An electrical component, likely the commutator or a worn brush assembly, generated a spark. The spark entered the shaft headspace, where hydrogen concentration had reached stoichiometric mixture, the exact ratio for maximum explosive force. Ignition was instantaneous. Hydrogen combustion propagates at 1800 meters per second in confined spaces. The reaction front swept through the headspace in milliseconds, converting chemical potential energy into overpressure. The shaft became a vertical cannon. Pressure spiked. The concrete lid, anchored by its own weight and minimal fastening, experienced an upward force exceeding its structural resistance. The gas expanded. The lid displaced. Then it launched. Eyewitness accounts describe a sound like a thunderclap. A plume of dust and debris erupted from the shaft opening. The concrete lid, weighing multiple tons, left the shaft in a ballistic trajectory. It did not simply lift. It was ejected with sufficient force to clear the immediate headworks and land meters away. Workers on site turned toward the sound. Some dropped tools. Others froze. The noise was wrong. Not the hum of machinery or the clang of construction. This was percussion. Deep, singular, the kind of sound that makes the chest cavity resonate. One technician later described seeing the dust cloud rise, grey, dense, expanding, and knowing immediately that something structural had failed. Not a valve, not a pipe, something massive. The explosion fractured the shaft collar. Steel reinforcement bent, concrete crumbled. The structural integrity of the upper shaft deteriorated in seconds. Site alarms triggered. Not radiation alarms, those would come later after dosimetry sweeps. These were structural alarms. Pressure differentials, ventilation disruptions, the kind of cascade that signals containment breach. Emergency response teams mobilized. Perimeter cordons were established. Personnel were evacuated from the immediate area, but the response was reactive, not preventive. The event had already occurred. The energy had already dissipated, and then silence. But silence in a nuclear facility is never reassurance. It's the prelude to measurement, to dosimetry, to the realization that what just escaped cannot be put back. The question wasn't whether contamination had been released. The question was how much and how far. The explosion lasted less than 1 second. The consequences are permanent. When the lid cleared the shaft, it carried with it a column of air, contaminated air, that had been in direct contact with 2 decades of radioactive material. Dust, metallic fragments, particulate matter coated in isotopes. The plume dispersed immediately. Wind currents carried it across the Dounreay site. Some particles settled within the facility perimeter. Others travelled farther, onto the foreshore, into the coastal vegetation, across public beaches used by residents of Caithness. The material was not uniformly hazardous. Most of the waste in the shaft was intermediate level, dangerous but not acutely lethal on brief contact. However, embedded within that matrix were high-activity particles, fragments of fuel cladding, reactor components, sodium residue, capable of delivering significant radiation dose. These particles are small, millimeters in diameter. Invisible to the unabled eye, they do not announce themselves. But they emit alpha radiation, beta particles, gamma rays. The dosimetry profile varies by particle, but the mechanism is consistent: localized, concentrated radioactive decay in whatever material or tissue they contact. The site response in 1977 was immediate in operational terms. The shaft was declared off-limits, all further disposal ceased, and damage assessment began. But the environmental response took longer, much longer. In the weeks following the explosion, dosimetry teams swept the facility grounds. Radiation detectors mapped surface contamination. Swipe samples were taken from buildings, vehicles, equipment. The perimeter fence became a containment boundary. Everything inside was suspect. Initial surveys detected elevated readings near the shaft. Expected, predictable, but as the monitoring radius expanded, anomalies appeared farther out. Hotspots beyond the facility boundary, detections on paths used by maintenance personnel, particles in drainage channels leading toward the coast. The contamination had migrated. In the 1980s, beach monitoring programs near Dounreay began detecting anomalous particles. Small, metallic, radioactive. Their isotopic signature matched materials used in the reactors at Dounreay. The correlation was undeniable. In 1995, the Committee on Medical Aspects of Radiation in the Environment, COMER, published findings linking the beach contamination directly to the 1977 explosion. The blast had not simply damaged infrastructure, it had seeded the surrounding landscape with a persistent radiological hazard. Recovery crews worked for years, sifting sand, scanning the seabed, removing particles one by one. But you cannot remove what you cannot find, and the search area is measured in square kilometers. The forensic conclusion is stark. A single second of overpressure created a contamination field that will require centuries to remediate. The explosion was brief. The cleanup is generational. The particles are still there. 2024. BBC News reports the discovery of a radioactive particle near Dounreay, the most radioactive find in 3 years. The monitoring program continues. The hazard persists. This is not negligence. This is physics. Radioactive decay operates on timescales that dwarf human planning. The isotopes released in 1977, cesium-137, strontium-90 americium-241, have half-lives measured in decades or centuries. A particle lost in 1977 will still be emitting in 2077. The environmental burden is forensic evidence written in isotopes. Dounreay's foreshore remains a controlled area. Public access is restricted. Monitoring equipment scans the beaches at intervals. When a particle is detected, a team is deployed, the fragment is extracted, analyzed, and disposed of through proper channels. But the inventory is unknown. How many particles were released in the explosion? Estimates exist, but no definitive count. The shaft's contents were never catalogued with precision. Disposal records from the 1960s are incomplete. Workers threw material into darkness and moved on. The consequence is a permanent liability. The Site Authority, now the Nuclear Decommissioning Authority, lists Dounreay among the United Kingdom's most complex remediation projects. The shaft itself is the centerpiece. Cleaning it requires remotely operated equipment, radiation-hardened robotics, and engineering techniques that did not exist in 1977. The task is not simply removing waste, it's removing waste whose exact composition, distribution, and radiological profile remain uncertain. Every operation carries the risk of disturbing material that has been static for decades, disturbing it and making it airborne again. Consider the operational challenge. Engineers must design tools capable of working in a vertical shaft where radiation levels spike unpredictably. Cameras fail under gamma exposure, electronics degrade, mechanical systems must be simple, durable, and remotely controlled from a safe distance. Each extraction cycle follows the same protocol. Lower the tool, secure a fragment, retract, package, store. Repeat, the pace is slow. The margin for error is zero. A dropped fragment, a contaminated surface, a breach in the remote handling system. Any of these turns a controlled operation into an incident. The Office for Nuclear Regulation describes the site as a construction, demolition and waste management operation, a decades-long industrial undertaking designed to bring Dounreay to a safe state for future generations. But safe is a relative term. The site will never be pristine. The best achievable outcome is containment, stability, assurance that the hazard will not propagate further. And that requires finishing what the explosion started, emptying the shaft. 2020. The BBC calls it the world's deepest nuclear cleanup. 65 meters below the surface, the shaft waits. Engineers have spent years developing a remediation strategy. The plan is methodical. Construct a containment structure over the shaft, deploy remote handling equipment, extract waste in controlled increments, package it for long-term storage, and decommission the shaft itself once empty. The timeline is measured in decades. The cost is measured in hundreds of millions of pounds. The difficulty is measured in unknowns, because after 18 years of disposal and 47 years of sealing, nobody knows exactly what's down there. Imaging technology provides partial data, radiation surveys map hotspots. But the full inventory, the precise chemical and radiological profile, will only be known when the waste is physically removed. And removal is dangerous. Reactive metals may still be present, pockets of hydrogen could have reformed. Structural instability from the explosion means the shaft walls themselves are a hazard. Every operation must account for the possibility of further collapse, further contamination release, further risk to personnel. This is not a problem that can be solved quickly. This is a multi-generational undertaking. The workers who disposed of waste in the 1960s are retired or deceased. The engineers managing remediation today will not see the project completed. The final decommissioning will be overseen by professionals not yet born. The forensic record is clear. A procedural lapse in 1959, repurposing a flooded shaft as a waste repository, created a chemical hazard. A systemic oversight, failing to monitor hydrogen accumulation, allowed that hazard to intensify. An operational trigger in 1977, activating a pump, provided ignition energy, and the explosion that followed distributed radioactive contamination across a landscape where it will remain for the better part of a century. Dounreay is not an anomaly. It is a case study in the hidden cost of industrial expediency. The decision to use the shaft was convenient, disposal was cheap, monitoring was minimal, and when the system failed, the consequences became permanent. The particles on the beach are still being counted, the shaft is still being emptied, and the timeline for full site clearance extends into the 22nd century. Think about the scale of that temporal debt. A decision made in 1959, an explosion in 1977, a cleanup beginning in earnest in 2022, and a projected end date sometime after 2100. That's 140 years from inception to closure. Longer than most nations have existed. Longer than any corporation has survived. Longer than any individual lifetime. The engineers tasked with final remediation will inherit blueprints, dosimetry maps, and contamination models, but they will never meet the people who created the problem. They will be managing the consequences of decisions made by the dead. And that is the true legacy of the Dounreay shaft. Not the explosion, not the particles, but the permanence, the inescapable arithmetic of radioactive half-lives and generational responsibility. The containment vessel that failed in 1977 was concrete and steel. The containment vessel that must succeed now is institutional memory, regulatory oversight, and the sustained commitment of multiple generations to finish a task that should never have begun. If you want to understand how industrial decisions made decades ago become environmental liabilities, measured in generations, subscribe to Forensic Protocol, because the next investigation reveals what happens when containment fails in plain sight.